All right, so let's go on page 107. We're leaving 106 blank, and we are starting transformations. So that includes reflections, translations, rotations, dilations. Those are all the transformations that are not brand new to you. You have talked about transformations for a long time. Very early on, they may have used the wrong words with you, like a flip, a turn, and a slide, but those things need to go in the trash can, right? But reflections, translations, rotations, and dilations. And I know that you do look at it kind of from an algebraic perspective in 8th grade math, which a lot of you took in 7th grade, but it's still 8th grade math content. And so a lot of what we're doing today is a review, and I will kind of explain to you why we care and how we're going to extend this and where this is going for you in your future. So let's start with some definitions. So this first definition is of a word that I'm quite sure you haven't heard before, but this is classifies a transformation that does not change the shape or size of a figure. So if I list them out again, reflections, translations, rotations, dilations, which one of those four does not fit in this category? Dilation, okay, because a dilation does change. Does it change size, shape, or both? Just size, not the shape, because they are similar figures after you dilate something, right? So it's not size and shape that changes, just the size. But because of that, it doesn't fall under this category. So this only includes for us right now translations, rotations, and reflections. And this is what's called an isometry, I-S-O-M-E-T-R-Y, isometry. What do you mean? Yes, yes, yeah. So he said that's what dilation is, like when your eyes get dilated, right? You can't have a circle that's not similar, but that's what's happening really. I mean, the circle stays similar because all circles are similar. But yeah, your eyes are dilated. They open them up so that they can look inside there, and it changes the size, but it does not change the shape. Exactly. All right, so isometries, those include, like I just said, they include the reflection, reflections, translations, rotations are all isometries because the motion from the pre-image to the image, and those words you should be familiar with as well, is rigid. Okay, so rigid meaning that we're not changing size or shape. So an isometry can also be called a rigid transformation. And again, the shape does not change. And then the shapes are what? If they do not change at all, it's not. They are similar, but more specifically congruent. Good. They are congruent. So you can refer to them as isometries, as rigid transformations, or as congruence transformations. Those all three refer to the same thing. Okay, so the first one that we're going to look at is a reflection. So a reflection is a transformation across a line of reflection such that the line of reflection is the perpendicular bisector of each segment joining each point in its image. And I'll explain to you after we do an example why it has those words in it, which might seem a little weird why we're talking about perpendicular bisector stuff, but it's more than just flipping it over a line, okay, which is maybe the only way it's ever been expressed to you. So we're going to start here, and it says we're going to plot and label the points A, B, and C on the graph, draw ABC, graph the reflection image over the x-axis, label the points. Now, how do I say that right there? A prime. So this is A prime. It's not A apostrophe. A prime. So we label them A prime, B prime, C prime, draw the triangle, record the coordinates. Okay, so we're going to start with just looking at the graphs. We're going to ignore the table for a minute. I already have the triangles there for you, so all you need to do is label them, and when you're actually having to graph it yourself, label them as you are plotting them. Otherwise, you may label them with the wrong letters, and then that just throws everything off. But if you look at what's given to you and we label them, this is A, B, and C. So it told us that we're going to reflect it across the x-axis, so you draw in your line of reflection. So here is my line of reflection. So my computer's behind. There we go. And then we're going to do it The super easy way, which I know you've done it differently than just this way already, and then we'll talk about it a little bit more, but if I want to reflect this in this line, we've already did that when we did revolutions. That's why I didn't bother teaching this first, because I know you've already learned this stuff. If A is 1 away on this side, it has to come 1 away on this side, so this is A prime. B prime is here. C prime is here. Then you use a straight edge of some sort and connect those to get your new triangle. And I missed the prime on these. B prime and C prime. Now let's talk about that whole perpendicular bisector thing. If I connect a point to its image, so I'm going to use B. I'm going to connect B to B prime. And I could actually do this for all 3 of them, but I don't want there to be too much on there. We'll just do it with B. When I do that, then this line segment that is created is perpendicular to the line of reflection, and the line of reflection bisects that segment, which should make sense, because isn't that how we got it? We counted down perpendicular to the axis 2, and we went 2 on the other side. For C, 4 and 4. For A, 1 and 1, right? And so it's in there because we're not always reflecting necessarily on the coordinate plane. I could give you a piece of paper that has a triangle and a line on it and say reflected in this line, right? And you may have done reflections with patty paper before and folding, but I mean, there's a mathematical way to it that's not folding a piece of paper. And you could, let's say that we were going to do that. Well, I can take my triangle and take a vertex and draw a line perpendicular to my line of reflection, measure that line segment, continue it that far on the other side, make my point, and do that for all of them. Then when I connect the dots, like we just did, then I should have a figure that is congruent to my original one that has been reflected over that line. Okay, so that's why that's part of that definition, because it's not about just counting on the coordinate plane. All right, so let's look at the second one. Let's go ahead and label that one. This is A, B, and C. I am again reflecting in the x-axis. So I'm going to draw that in. Oh, goodness. Okay, so get that reflection drawn. There we go. So sometimes they overlap, and that's okay, right? Here on this first triangle, none of the points on the triangle were touching the line of reflection, so in the end, none of them were touching. If you have any that are actually attached to the line of reflection, then they just remain there. And I feel like did I plot one of my points wrong, or does it just look weird? Oh, dang it, A is wrong. Okay, yes, you know what? But you know how I caught that? As I was saying that, I was looking at this. First of all, they don't really look congruent, right? And these points should have stayed right where they were. So I can tell that I have a mistake there. I just plotted the point wrong. So let me undo all this. And of course, it was the first one I did, so all the way back. I had it too, yeah. I didn't count right. I wasn't paying attention. No, that's, you need to call me out, though. That's... All right. That's right. Okay, so now I can tell that I am right? Because as soon as I looked, I didn't really look at what I was doing. When I looked at it, and I was saying that to y'all, I knew something wasn't right. But do you see how these, the same point is still attached because it gets flipped around? So it was actually a good thing that I messed up, so I could kind of point that out. It's a good way to catch your own mistakes sometimes. Okay, we good with that? Now I want you to take what you have, and you are going to go ahead and get these points and write them into this little chart up here, what your image points are for the prime points. There is, and we're going to talk about it in a minute as soon as you fill it all out. Okay, so I heard things like, I remember this, there's a formula, we did this. Yes, you did, and you should know it because this is totally 8th grade math, okay, which again, a lot of you took in 7th grade. But so when you look at what's happening here, if you look at your pre-image points and your image points, something changes and something does not. So when you reflect in the x-axis, what does not change? The x value. If I'm reflecting in the x-axis, the x value does not change. What happens to the y value? Ooh, that word opposite needs to go in the trash can. Okay, you get multiplied by a -1 or you change the sign, but opposite, I really don't know what that means. Okay, so it could opposite of what, right? It doesn't make any sense. So it's that's okay. I mean, that very well could have been how it was said to you when you learned it. I don't know. That's just not a good way to describe things moving forward because opposite can mean a lot of things. So you change the sign or you multiply it by a -1, either way. Now, we're only going to talk about reflections today and what those rules are, some of which will be new to you, most of which you will already have remembered. But after we get all the rules down, the reflection, the translation, the rotation, on some of them, the signs change, some of them they don't, and then they all start to kind of look the same. And so it's possible that when you go to do it, if you don't have a graph, I could just go ahead and get my points. I don't need the graph if I know what the rule is, but sometimes you second guess yourself on the rule, right? So if you want to make sure that you have it right, because they all look so similar, that's why I try and get you to draw these little ballpark graphs like, all right, so I'm just trying to wrap my mind around the rule. If I have this point, whatever it is, and I'm going to reflect it in the x-axis, it's going to end up down here. So then you can look at that and know, all right, well, it's the x value that clearly doesn't change, it's the y value that does, and that way you can be confident that you have the right thing that you're using. You with me on that? Okay, now, let me ask you this. Because the whole idea of this is not for us to be able to move polygons around on the coordinate plane. Yes, sir? Yes, and we're getting there. So where we're going with all of this stuff is that I mean, yes, okay, I might need to actually move polygons around the coordinate plane, but we're getting to a functional aspect of this, to look at our functions. Transformations are huge in Algebra 2 and Pre-Cal and Calculus and beyond, but we're not transforming triangles necessarily. We are looking at the functions, and it's the same stuff. And I don't know that students always make that connection, and I don't know if that connection is always made for you. But that's why we're doing this stuff now. So let's just think about this. If I'm going to graph y equals x squared, when you graph that, what does it look like? What is that called? It's a parabola. Okay, and not only is it a parabola, this is the parent function of a parabola, right? So it would look like that. And so what if I was to graph y equals -x squared? What does that look like? Okay, it's reflected over the x-axis. Probably, I would guess, especially when you first learn parabolas, I don't know, because you don't really talk about transformations that much in Algebra 1. You do a little bit, but not a whole lot, so I don't know how much time they have to make those connections. But you're probably really more talked about it as opening up or opening down, right? But what I want to make sure that you understand what's really happening is it is a reflection in the x-axis. And all that is happening is that you are changing the sign on the y value. When you substitute in x on either one of these, x is whatever you have x as. If it's a 3, it's 3. So you substitute in 3, x is 3. Y is 9, right? I substitute in 3 here, x is 3. But after I square it, it becomes negative, and so then I get a -9. So even though the sign is on the x, it's actually changing the sign on the y. Does that make sense to you? And that's all that is a reflection across the x-axis. Okay? And that's how you look at these functions and how you have to make sure that you understand them. So the rules that we're getting from the polygons are important to understand to be able to apply to things moving forward. Okay? So let's take that and fill in this next part here. And it says, as soon as it wants to turn, come on, there we go. It says, using the results above, which is really on the last page, if P is at AB, what are the coordinates of P if it's the reflection image over the x-axis? So AB would become what? A negative B, because we just changed the sign on B. Now, the notation that is important that you understand is this notation here. which you may or may not have seen it in such a fashion. I'm thinking you have, because that, again, it's in the TEKS for 8th grade math, and it's on that STAR test. So I would be willing to bet, yeah, that's exactly what you've seen. But do you know how to say that? No, probably not. Now, you do? Say it. Okay, but that's a good guess. The whole if, because it kind of looks like the if then, right, with the arrow, and it's not. In a way, you can kind of think of it that way. But remember, that's symbolic logic and that's symbolic notation, and it's good that you remember that. But that has a whole separate set of notation and rules than this stuff does. Now, you could think of it as if I start with this point and then I reflect it, then I end up with that. So I mean, it's still kind of that, but that's not how you read this or what's happening. What this says and how you say this is that xy maps to x negative y. So this point maps to its new point. If you just think of it this way, you are literally looking at a map and you're trying to figure out how to get from one place to other. You're about to map yourself from one point to the other. That is what is happening. And so these transformations, they are mappings. We are mapping one point to another. How do we get there? We get there this way with the reflection. Okay? That makes sense to you? So that whole maps to thing is an important thing to understand. All right, so now let's look at the graphs for this one. In this one, we are reflecting across the y-axis. So we're going to start by labeling these points first. A, B, C. I'm going to draw in my line of reflection, which is the y-axis. And then I'm going to reflect, hopefully correctly this time. And then go ahead and do the same thing for the second graph. Oh, I didn't draw in my line of reflection. Alrighty. There we go. All right, so those are almost identical. I don't know that we necessarily needed two of them, but if we go and fill in the ordered pairs for the first graph, then it's going to give me 3, 2, 4, negative 4, 3. So what is this rule? Which you should already know. What doesn't change? No, what doesn't change? The y value. And what happens to the x value? Multiply by a negative 1, or you change the sign. Now, so what if I can graph my green triangle and then come up with my ordered pairs, right? Or I can come up with my ordered pairs without graphing it. Or if I have to do both, I usually do both. Like from my graph, I usually just do it by looking and counting if it's something simple. And then from here, I just go ahead and do the points using the rule. And then you can double check yourself and make sure you didn't graph something wrong or get something else wrong. But since I'm reflecting in the y-axis, the y value stays the same. And you change the sign on x. And it looks like that. We all good with that? Mm-hmm. All right, so here says what are the coordinates of P prime and the reflection over the y-axis. So then point P would be what? negative a, b. And in my mapping notation, we would say xy maps to negative x, y. Oh, yes, thank you. T prime. I know. Golly. Oh, no, Amy's rubbing off on me. All right. Okay. So now we are going to do the same kind of thing, but this time we are reflecting across the line y equals x. Okay. So let's just start with the graphs again. Label our vertices. This would be A, B, and C. And we are reflecting across the line y equals x. Is that an easy or difficult line to graph? Easy. If you still don't know how to graph that line, we need to have a serious conversation about your math placement next year, because I may send you back to Algebra 1 or pre-algebra, I don't know. So draw in y equals x. What is that thing called? The parent function, yes. So I draw in the parent function, and now we're reflecting, and I think this is what you were asking, Jacob, across something that has a slope that's not vertical or horizontal. Now, are you allowed to count diagonally the same way you're allowed to count vertically and horizontally? No. Now, you can count diagonally in a way, all right? It's not the same. It's not one unit. You know, I can't really count that way, but I can find distances. So I want you to think about it this way. If I have point C, now from the definition of a reflection, the line segment that connects C and C prime has to be perpendicular to the line of reflection. Well, my line of reflection goes through the diagonal in this direction. If I go through the diagonal in the other direction, that would make them perpendicular, right? Because those are the diagonals of a square and they're perpendicular. So if I count diagonally, this isn't one unit, but it is one diagonal, right? So if it takes me one diagonal to get to the line, I go one diagonal on the other side, there's C prime. Tell me about A prime. It's the same thing. Good. Yep. And then so B, it takes me two diagonals to get to the line, so I go two on the other side, and that's B prime. And then I'm going to connect them. And then we are going to do the same thing on the next graph, because you got to count a little bit differently on this one, and I want to make sure that you understand how things change a little bit. A, B, and C, and then I draw in a line of reflection. So now, when I go to get A is only half a diagonal to get to the line, so I go half a diagonal on the other side, that's A prime. Now, when I did B over here, I actually counted along the side length of the triangle, but that was a coincidence. That's not what we're doing. I don't count along the diagonal of the triangle. I have to go perpendicular to the line, so I have to go across the diagonals of the squares. So it would take me 1.5 diagonals to get to the line. So I go 1.5 diagonals on the other side to get C prime. So from C, perpendicular to the line, there is 1.5 diagonals. So I have to go 1.5 diagonals on the other side. B, it's one diagonal. Don't count along the line segment because you can't. You go diagonally through the square. You get 1, so you go one on the other side, and that is B prime. Now, is this counting as easy as the others? No, it can actually get kind of confusing depending on the picture, all right? So let's look at, here's what I want you to do without saying anything to anybody, bless you, because this isn't something that's a review, because you've reflected and know the rules for X and Y axis, but not this line. I want you to take the ordered pairs that you have gotten from your graph, and I want you to write them in the charts and think without speaking, give everybody processing time, look at what you think the pattern might be, and then when you figure it out, do your best to keep your mouth shut and just hang on for everybody to have time to process. Okay, so go ahead and fill in the points from your graph. All right, so who wants to tell me, Braden? Okay. Well, the points switch. The points switch with what? No, okay. What switches? The points? Amy? Yes. No, go ahead. Okay, good. And it's the coordinates. The coordinates are you could say the X and the Y switch or the coordinates. That was the word, not the points itself. Like, I know what you mean. That's another thing. And that's why I'm trying to help y'all with this, because usually I know what you mean. I know what you're trying to say. But when you start having to write a whole lot more in math, which you're going to have to, you have to make sure that you can express what you're really thinking. So it's the coordinates that switch places, or X and Y, they just switch places, right? X becomes Y and Y becomes X. So the way to remember it is it's the line Y equals X. So if X equals Y, Y equals X. X and Y, they just literally switch places. And this right here is a transformation that you're going to use a lot in Algebra 2, because this is actually how you get the inverses. If I was to graph a function, let's say that this was a function. So I graph this function. This is the inverse of that function, because the inverse is a reflection over the line Y equals X. When you want to find it algebraically, you take an equation and you change places for X and Y. So for instance, if I do Y equals X squared, right, then we know that that's this. Now, I don't think that you have done this yet, but if I wanted the inverse of that, then X and Y change places, so that would become X equals Y squared, right? And when you graph that, it looks like this. And all that is a reflection in the line Y equals X. Okay? That's the reflection. X and Y switch places. And literally we only had 3 vertices here, but there's an infinite number of points on the triangle. There's an infinite number of points in the parabola. And it's just an inverse. Okay? Does that make sense? Okay. Now, and unfortunately, there's a lot that you do that you have already learned, and a lot we do in geometry that truly really does connect to things that you're doing here in the near future, but I don't think you always get those connections, and that if you do, then it makes everything make a little bit more sense. All right, so if we're reflecting it in the line Y equals X, then P prime would become what? BA. Good. So then my mapping notation, XY maps to what? YX. All right, so now let's just sum this up here. If I'm going to reflect across the x-axis, right, then here's my line of reflection. It is perpendicular to the segment that's created here, and it bisects this little segment. When you reflect in the x-axis, the x value remains the same, and the sign on the Y changes. If it's negative, it's not positive. If it's positive, it's not negative. Across the Y-axis, this is my line of reflection. It's perpendicular to this little segment, and it bisects it. So when I reflect in the Y-axis, one second. There. I covered up my prime. When you reflect in the Y-axis, the Y value stays the same, and you change the sign on X. When I reflect across the line Y equals X, that's this line here, and then all the numbers remain what they are. Their placement just changes, because there is a rule that we will get to for a different type of transformation where they switch places and a sign changes. So we got to make sure we get all this straight. So your mapping notation, XY for when you reflect across the x-axis. XY maps to X negative Y. Good. When you reflect across the Y-axis, XY maps to negative XY. When you reflect across Y equals X, XY maps to YX. Very good. So make sure that you have a good grasp on these 3 so that when we get the other ones, they don't start to all get mixed up in your head. Find a way to make sure that this is solidified in there for you. Okay? We all good? Any questions? All right. All right, now look at the assignment I just gave you, right? On 1 through 4, the key word on 1 through 4 is appears, because it says tell whether each transformation appears to be a reflection. I know it doesn't tell you that things are actually congruent or not, but you can tell if what's happening is supposed to represent a reflection. Okay, so you get to assume a little bit about congruence. On 8 through 11, it says, reflect the figure with the given vertices across the given line. Down at the bottom, I have made that a little bit more clear. It says, write the ordered pairs for the vertices of the image and the mapping next to the graph. Make sure you graph and label the pre-image and the image. So what I mean by that is all of this should be graphed and labeled. You have to have both figures, line of reflection, all the primes and all that good kind of stuff. And then it also says, write the ordered pairs for the vertices of the image. So you have to list this out to the side. It's not enough just to put it on the graph. Okay, list these out to the side and write the mapping, which is this right here. Okay, does that make sense to you? So all that stuff needs to be written out to the side there. The back, I believe, is pretty self-explanatory, except on number 13, I don't even really know how this happened, but there's a word in that sentence that's in parentheses, left, and then it's marked out. I think I was trying to delete it. I don't know how it just got like crossed out digitally. But anyway, that's not even supposed to be there. That's why it's crossed out. So just ignore that. Okay. I don't even know how I did that. Yeah. 1 through 4 is just yes or no. All right. We good? Awesome.